Okay, hi everyone. Good evening. Well, good morning for you all, and hello, Dr. Schumacher. Let's everyone say hello to her and thank her for helping out this morning. Everyone, we are going to learn about a new method of approximation called Euler's method. Before I continue, let's make sure that everyone handed in your take home to Dr. Schumacher. And I know a number of you are wondering about your tests, and I so apologize. They're still sitting on my desk and they're almost done. But as you know, I have not been in all week. And the intention was to have these back to you on Monday. And so just please be patient as I kind of get my stuff all in order and deal with, the unexpected that inevitably comes up. Okay, so you should have your notes there, and I think that you may have. This is the second page if they were stapled. Maybe it's two-sided what you have, but I want you to be on this page right here. So Euler's method is a method of approximation. Okay, it's the purpose of Euler's method is to approximate function values. So it is a method of approximating. It's a method of approximating f of x given f prime of x and a known point. Whoops, given f prime of x, given f prime of x, a step size, or dx, and a known point. Oh my goodness, sorry, I'm having some issues with my computer here. Okay, and a known point. Okay, the only new vocabulary that you're going to see is this that word I just used. It's called step size. And when you are wondering, or when you read step size, all you need to know is that step size is no different than just dx, okay? Or the run, okay? The change, okay? The change in the independent variable. I'm sitting at my lovely desk and working space, and one of the things I realized is that I'm so incredibly distracted by all the kind of tchotchkes surrounding my space that even though I'm sitting here knowing full well that I'm live and I could be streaming to millions of viewers, I'm still just so very distracted, and my hand wants to go and grab this little bobblehead and play with it. It's Sidney Crosby. Okay, the change in the independent variable. Okay, I'm going to come back to this statement here about precision, because I think after we work through it, you're going to be able to tell me what precision depends on. So let's just make sure we kind of regroup and just understand this idea of approximating. We've actually been approximating function values since the very beginning of calculus. The local linear approximation, for example, was the first time you used a line in that case to approximate a function. Once you start talking about approximations, you can then talk about over or under approximations. You can talk about error, and of course, then that brings in graphical features like concavity. And whether the function's increasing or decreasing, so once you start approximating functions, you begin to ask yourself, well, are there better approximating methods? The local linear approximation is one way to approximate. This is another way. We will end BC Calculus with our probably most challenging unit on series, and we'll talk about local quadratic approximations and local cubic approximations, and ask ourselves the very question, really, if the approximating function of f of x, if it's a polynomial, is it true that the higher the polynomial's degree, the better the approximation? So this idea of approximating is really an old one. But what I want to do is just show you how Euler's method works, and then come back to this question. What does the precision of this method depend on? Okay? All right, so here's kind of a classic question. A question looks like this. It says, Consider the differential equation dy dx equals x times y minus 1 squared, and you are given y of -1 equals -1, or you're given a point on the antiderivative, or on the function f of x. And dx equals 0.5. And here is again, this question used the phrasing dx, but sometimes you'll see something like you are given y of -1 equals -1, and dx, or step size, equals 0.5. So these two words, if you will, are synonymous, okay? Use Euler's method to approximate y of 0.5. Depending on how awake you are, some of you may look at this differential equation and say to yourself, why would we ever want to approximate when I can actually find the exact function? I'm going to give you 2 seconds. Just look at your neighbor who may be 50% awake and just say, why is Miss Yam implying that we could actually find the function here? And then just come back to me and replay me. Okay. So hopefully you've had that conversation using your mouth and not just kind of, like mental transmission. But if you look at this differential equation, it's separable, right? So I could divide both sides by y minus 1 squared and multiply the dx over. So I purposely gave you here a differential equation that, quite frankly, we would never need to use an approximation because I could actually find the function, right? Which leads to the larger point. The more general point is, generally speaking, we use approximative methods like Euler's method and we can't find the exact function. But the reason why I did so here is because I want to actually do a comparison in the end between my approximation and the actual true value, okay? All right, so let's set up Euler's method. So here's the question. Use Euler's method to approximate y of 0.5, okay? So I'm given the y value -1 when x equals -1, and this question here is asking, what will the y value be when x equals 0.5, right? So I want to find what the dependent variable will equal at x equals 0.5. So here's how Euler's method works. Euler's method is an iterative process, okay? Iterative really means repetitive, okay? Iterative means you do something procedurally, sometimes several times, repetitive, all right? So the way I like to use Euler's method, I first like to set it up. I like to set it up, and I set it up this way. I kind of start with the point, and then I go over here and I'm just going to write this differential equation where it's solved for y, okay? So I start here. So I know that, oops, my goodness, dx, goodness, there's dx, okay? Now we're told that dx equals 0.5, all right? So I'm going to do this. I'm going to drop dy equals x, we know the value for x at this point is -1. Y is also -1. Dx is 1/2, or 0.5. So what I'm doing here, everyone, by subbing in a known point and dx, I'm getting a dy. I'm going to ask you what this is in a second. I'm going to clean this up. This becomes -1 times 4 times 1/2, and I get -2. Okay, so dx, let's walk back up here. Dx is the run. Dx is the change in the independent variable. You don't have to write this part down with me here, but you may have remembered last year in BC Calc Part 1, you may have done this, or TIC. You certainly did this in AB, okay? If I have a function here, and I have the tangent line, here's the purple tangent line, right? If I were to move from this point of tangency to the right, and I look at the rise, there are 2 different rises, right? This run, dx, is the run of the tangent line. The corresponding rise of the tangent line is what we call dy. This is why dy dx, one of the reasons why, this is why dy dx is known as the slope of the line tangent, right? Slope of tan. Okay? But there's another change in x and change in y, and that looks like this. So change in x, and look at this change in y. The run of the function, if you will, we call it delta x. The rise of the function we call delta y. And you'll probably look at this picture and say, oh, but dx and delta x are always the same, because if you look here, everyone, right, when I travel from here to here, that is the run of both the tangent line and the function. So yes, dx always equals delta x. dy and delta y, however, don't always equal each other. And you'll agree, I hope, that as dx or as delta x approaches 0, dy and delta y become closer together. In other words, dy better approximates delta y. But this understanding, really, Euler's method, is based on remembering that dx and dy are no other than the rise and the run of the tangent line. So let's walk over here for a minute. We just found that at the point -1, -1, dy is -2. What was dx again? Oh, dx was 0.5. I'm going to write this down. dx was 0.5 and dy was -2. Now I'm going to go over here and ask you this question. Let's go back to my little drawing. Now that I think about it, I think this drawing is pretty darn good. Maybe this here was the point -1, -1. I mean, be a little bit loose with me here and don't take obviously my quadrants literally. Maybe I'll erase that if it'll bother some of you. Perhaps it bothers some of you. Okay, fine, all gone. So maybe that point -1, -1 was right here. Well, what I just did was I found the dy. Can you see my pencil right here? I found the dy. The dy was this value. And I knew the dx. The dx was this value. What could I do if I added the dx and the dy to -1, -1? I get this point. And this point is a close approximation of the function f of x. Okay, so what I'm going to do here is I'm going to say, well, I started at this known point -1, -1. Let's add the run to -1. And let's add the rise to -1, and we'll get this point. So let's see what happens. If I go here, and I add dx and dy to this point, I get a new point. And what's my new point? My new point would be, let's see, -1 plus a half. Yes, -0.5, comma, -1 plus -2. It is -3. Now you have to be very, very careful. It would be absolutely wrong to say that y of -0.5 equals -3. No, we're not saying, let's go back to my drawing, we are not saying that it is a point on the function. What we're saying is y of -0.5 is approximately -3. Does everyone understand me? Okay, very good. And I like how you were kind of able to follow me, even though I was like adding a negative run here, right? Well, actually, I just said I like how you're able to follow me. I actually have no idea if you could have followed me, but oh, that's the gamble we make in these non-face-to-face screencasts. Reason number, I would say 100, why I don't think teaching could ever become mechanized, but that's neither here nor there. Okay, am I done? Let's see. No, I was asked to use Euler's to approximate y of 0.5. I'm now at y of -0.5. So I have to do this process again. And not only do I have to do it again, I have to do it again. And this is my new point, right? And what's interesting is, I think you probably see here, oh no. Oh no. Wait, hold on.